Yes, my screen is visible. Respond.
Yes, sir.
Okay. Now we will go further. Yes. Yesterday we discussed about the Hall effect. So once again, briefly, I will explain the Hall effect. Okay. See here. So here, in case of Hall effect, application of the Hall effect. By using Hall effect, we will explain the carrier concentration. Either it will be P-type semiconductor or N-type semiconductor. That may and how many charge carriers will be present in that. Whether it will be metal or semiconductor also we can explain. Okay. So let us take here. So any semiconductor or metal, any semiconductor or metal. Now some current is passing in that specimen here. So the current direction will be x direction. Now if you apply the what is that magnetic field perpendicular to the current passing through the specimen, current passing through the specimen, that applied magnetic field direction will be perpendicular to the current direction. So then what happen according to the Hall effect? So electric field, that means potential will be developed. Potential will be developed. That the direction of potential will be perpendicular to the both applied magnetic field as well as current, Okay, this is about the Hall effect. Okay, so now here we are taking one specimen, current is passing according along the x direction. Now we will apply the magnetic field along the z direction. Z direction is nothing but outside the screen. So outside the screen. Okay, applied magnetic field direction is outside the screen. Now what happen according to the Lorentz? According to the Lorentz, if any suppose if any current is passing through the circuit, if you apply the magnetic field, so due to that magnetic field, some forces occur on the charge particle. Whatever the charge particle will be there inside. Who is that? So magnetic field will, if you apply the magnetic field, so what happened due to that magnetic field, force will be occur on the charge carriers. That force direction is so perpendicular to the both magnetic field as well as current direction. Okay, so due to that force, what happened? So here charge carriers move so either downwards or upwards. In this case, so current is passing x direction, magnetic field is applied, so z direction. Okay, so now so due to that magnetic field, some forces occur on that charge particle. So that force will direction will be downwards direction. How we can say that that is downward direction means so based on the, so let us take the left hand rule. So keep your three fingers perpendicular with each other. So thumb finger, index finger and middle finger. Okay, so perpendicular with each other. So here, so thumb finger shows the force direction and index finger shows the magnetic field direction, and middle finger shows the current direction. If you place the middle finger in current direction and index finger in magnetic field direction, so remaining finger gives the direction of the force. So take the left hand. So three fingers are perpendicular with each other. Okay, so simply how to remember which finger denotes which one means FBI. F means force, B means magnetic field direction, I is the current direction. FBI, thumb finger. So F, so index finger B, so middle finger I, FBI. So remember this. So based on this left hand rule, so we can find out the which direction what is that force will be occurs. So due to, so that force direction will be, so here the y direction, so negative y direction, that means downward direction. Okay, so due to that, what is the force here? F equal to BeV, that is due to magnetic field. So force occur on a charge particle. Here B is the applied magnetic field, E is the charge of the charge carrier, either it will be electron or hole. Okay, and v is the velocity of the charge particle. Either so it will be electron means that is the velocity of the electron. It will be hole means velocity of the hole. F equal BeV. Now, so here charge, so suppose we are taking electrons here, so electrons are coming downwards, so due to that what happened, some potential difference will be developed, so electrons are coming down. Okay, so that's why, so negative charge will be what is that, so accumulated on this downwards direction. Okay, so that's why, so positive, some positive charge will be accumulated on upward direction. So due to that what happened, some potential difference will be developed. So due to that potential difference, some electric field will be occur. So due to that potential difference, some electric field will be occur. So that electric field will be EH. So that electric field we will call it as Hall electric field. That electric field will be so EH. Okay, so that electric field direction is negative y direction, y axis. So and so due to that electric field, some force acting on the particles, charge particles. So that force is equal to due to electric field. So what happened, that force occurs is E into EH, E into EH. Now, so at equilibrium condition, upward force due to electric field is equal to the downward force due to magnetic field. Okay, so at equilibrium condition, if you will take FB is equal to FE, so both are in opposite direction. Both are in opposite direction. That's why I am taking minus here. So BEV is equal to E into EH. Okay, so here EE gets cancelled. So now finally, yeah. So finally, velocity of the electron V is equal to EH by B. Velocity of the electron V is equal to EH by B. Okay, here minus symbol will be there. Now coming to the current density formula. Current density formula, J is equal to NE into V. So NE into V. So from this equation, V is equal to J by NE. We can equate, so this above equation 1 and so this equation 2. Okay, if you equating both, so we can get the EH by B is equal to minus J by NE. From this, so we can calculate the EH value. EH is equal to minus JB by NE. Let us take, this is equation number 3. Okay, now here, so 1 by minus 1 by NE is called as coefficient, some coefficient, that is the coefficient is Hall coefficient. So Hall coefficient RH is equal to minus 1 by NE. Okay, let us substitute that RH value in this equation number 3. We will get EH is equal to RH into B into J. Okay, here. So from this equation, so we can get EH is equal to RH into B into J. So here we know that all terms, EH is the electric field, RH is the Hall coefficient, B is the applied magnetic field, J is the current density. J is the current density. From this, so we can calculate the RH value. RH is equal to EH by BJ. EH by BJ. Okay, now so we can write this EH in, so this EH is the electric field. That electric field in terms of what is the potential difference. Okay, here VH is the Hall voltage or Hall potential. Okay, so there is a relation between so voltage and electric field. V is equal to E into T. T is the thickness of the sample. So what thickness of the sample or specimen. So whatever we are taking, so now V is equal to E into T. Okay, therefore VH is equal to EH into T. Okay, this is about the what is that Hall voltage, and so finally, so here EH, there is a relation between so Hall what is that electric field and Hall voltage, that is EH is equal to VH by T. Okay, let us take, this is equation number 5. Okay, now so area of the sample is equal to A is equal to B into T. B into T. Okay, B is the breadth of the sample and T is the thickness of the sample. Okay, thickness of the sample or thickness of the specimen. Okay, now so current density J is equal to, so we know that current density, what is the formula for definition of current density? Current passing through the unit area is called as current density. J is equal to I by A. Now let us substitute the this A value in this equation. Therefore, J is equal to I by BT. So B into T. Now, so from this equation, RH is equal to Hall coefficient, RH is equal to EH by B into J. Okay, we know that EH value from equation 5 and we know that J value from equation 6. Substitute this EH and J value in this RH equation. In this RH equation. Okay, therefore, so RH is equal to VH by T by, so B into I by BT. Instead of J, I by BT we wrote here. Okay, if you simplify this equation, okay, VH into B by, so B into I. So let us take this is equation number 7. This is called Hall coefficient. Hall coefficient. So experimentally we can calculate the Hall coefficient by using this parameter. So VH is the, so Hall voltage we can measure by using voltmeter. So B is the width of the sample, and so capital B is the applied magnetic field, and I is the current passing through the specimen. Okay, so by using ammeter we can measure the I, and so we know that so B is the we are applying, so we know that what is the applied magnetic field. Okay, so all parameters are we know that, so that's why by using this, so we can calculate the RH. Okay, so now this is the Hall voltage. There is, so Hall voltage VH is equal to BIRH by B. Okay, so this is about the Hall effect. Hall effect. So what is the application of Hall effect? Okay, now here, so there are some applications of Hall effect will be there. So it will be used as a sensor. It will be used as a sensor. Okay, by using Hall effect, we can measure the how much magnetic field we applied. How much magnetic, we can measure the, so how much magnetic field we applied. Okay, so if you vary the so magnetic field means we can by using, so we can easily we can measure the, see here. So RH we can find out initially, and if you, we know that by using voltmeter we can measure the VH value. So that's why we can easily measure the varying magnetic fields. Varying magnetic fields. That's why we can use the sensor. Okay, now so determination of the type of given semiconductor. So this is which type of semiconductor we can also measure. Okay, now here for N-type semiconductor, Hall coefficient will be negative. For P-type semiconductor, Hall coefficient will be positive. So depends on that. So we can measure here. So whether it will be negative or positive. Okay. So now, so the next one is to determine the carrier concentration. So how many charge carriers will be present, whether it will be holes or electrons. So we can measure the carrier concentration and determine the mobility of charge carriers. So by using this equation, okay, we can measure the charge carriers concentration. So already we know that this equation, sigma equal to Ne into mu. Sigma conductivity, sigma is equal to Ne into mu. So from that equation, mu is equal to sigma by Ne. But we know that 1 by Ne equal to RH, Hall coefficient. So mu is equal to RH into sigma. So by using this equation, we can calculate the mobility also. This is the application of Hall effect. Okay. Now coming to the generation and recombination of charge carriers in semiconductor. Okay, so based on this generation and what is that recombination, we will explain the PN junction diode. That's why we are discussing about here. So generation and recombination of charge carriers. Okay, first of all we will discuss about the generation of electron or electron hole pair. Okay, electron hole pair. So already we know that, already previously only we discussed about this. So once again we will discuss this. So when sufficient energy is given to the semiconducting material, covalent bonds are broken and free electrons are raised from valence band to conduction band. Okay. Uh, Suppose if you will take any semiconducting material, so if you will take intrinsic semiconductor, let us take intrinsic semiconducting material. In that, so suppose silicon or germanium are the best example for intrinsic semiconducting material. If I will take silicon atom means, so that silicon atom is surrounding with the covalent bond with the surrounding silicon atom. So that's why what happened, so valency electrons also, so covalent bond with the surrounding silicon atom. That's why, so if you want to break the, so that bonding means we need particular energy. If you supply the particular energy, So particular energy, so required energy, simply required energy. So what happens, these bonds will be breaks, covalent bonds will be break, and the electron will goes to the, what is that, valency bond to conduction band, valency band to conduction band. Okay. If electron is going to the valency band to conduction band means what happen, hole will be left, hole will be left behind for every excess electron carrier. Okay, so if one electron will be, so jump from valency band to conduction band, what happen, hole will be formed, hole will be formed. So this is called as, so what is that, carrier generation of electron, whole pair. So if electron is jumping from here valency band to conduction band means, so in conduction band electron will be present, in valency band hole will be present. Okay, so that's why what happened, so pair of electron hole will be generated. Okay, so this is called as, so pair production. Okay, so pair production. Okay. Now, so recombination. So here, so if you give sufficient energy, that energy is which type of energy, either thermal energy or electrical energy, or so photon energy also, photon energy. So particular, so any type of energy we can give. So depends on that. If you give the any energy, what happens, that electron will goes to the valency band to conduction band. Okay. Now coming to the recombination. Recombination is said to occur when one of the conducting electron is bound again to the normal covalent tetrahedral site. This is called recombination. See here. So now, so in this conduction band, electron does not stay more time. Electron does not stay more time. After certain time, what happens? This electron comes to the valency band and recombine with the hole. Recombine with the hole. In this process we will call it as recombination of electron hole pair. Okay, so in conduction band, electron does not stay more time. After certain time, what happen? Electron comes to the valency band and recombine with the hole. Recombine with the hole. In this process, what happen? So there is a energy difference between the conduction band and valency band. Suppose valency band energy is E1, conduction band energy is E2. Okay, so what is the energy difference between conduction band and valency band means E2 minus E1, E2 minus E1. Okay, suppose if electron is recombined, if electron is recombined to the hole, what happened? Energy will be generated. So previous process, so what happened? So energy is absorbed. Energy is absorbed to, what is that, to move from electron, to move electron from valency band to conduction band. What happened? So here energy is absorbed. Energy is absorbed. But in case of recombination, what happened? So electron is jumping from higher energy state to lower energy state, higher energy state to lower energy state. That's why here energy is released. Energy is released. Okay, so in the presence of, in the recombination process, what happened? Energy will be released. Energy will be released. What is the energy means? That depends on the energy gap between the valency band and conduction band. That equal to energy released h nu is equal to, so E2 minus E1. Energy released h nu is equal to E2 minus E1. E2 is the energy of the conduction band. E1 is the energy of the valency band. Okay. Now, so in this process, what happened? Energy will be released. Okay. So that released energy depends on the energy gap. Energy gap is E2 minus E1. Okay. Now coming to the PN junction diode and Zener diode. So first we will discuss about the PN junction diode. Okay. Yeah. So PN junction diode we are discussing here. So in case of PN junction diode, so there are P region will be there as well as N region will be there. So in case of P region, what are the majority charge carriers? Holes are the majority charge carrier. Similarly, in case of N region, what are the majority charge carriers? Electrons are the majority charge carriers. Okay. So how to form PN junction means, so while metallurgical process, we can join the P region and N region by using metallurgical process. So if you join directly so P and N regions. So at room temperature means doesn't occur anything. Doesn't occur anything at higher temperatures. At higher temperatures are while preparing the material. While preparing the material, so one direction we will dope with P-type semiconductor. Another direction we are doping the so pentavalent. One direction we are doping the uh, trivalent material. Okay, so like that process. So what happened? So this PN junction will be formed. PN junction will be formed. Okay, so by using metallurgical process, we can make the PN junction diode. PN junction diode. Okay, so there are two ways are there. So how it will be means, so one N-type semiconductor, P-type semiconductor join directly at higher temperature by using metallurgical process. Okay, that is the one way. Now another way is while preparing the semiconducting material. So in one region we are doping with the so trivalent material, in another region we are doping with the pentavalent material. So because of that process, what happened, we can make a PN junction diode. Okay, how junction will be formed, we'll discuss here. So here, since N-type region has high electron concentration and P-type has high hole concentration, electron diffuse from N-type material to P-type material. Similarly, holes move by diffusion from P-type material to N-type material. Okay, see here. So how diffusion will be takes place. So what is the diffusion will be takes place means, diffusion will be takes place from higher concentration to lower concentration. Okay, so in this region, if you will take right side region, so majority charge carriers are electrons. So majority, that's why density of electrons will be high. So that's why these electrons try to move to the P region. Similarly, so in P region, what are the majority charge carriers? Holes. Okay, so these holes try to diffuse from so P region. Like suppose if you will take two gases, so you kept two gases in a one bowl. Okay, so what happened, so they will diffuse from one region, so one gas to another gas, okay, so like that only here also electron diffuse from so N region to P region, holes diffuse from P region to N region, okay. uh, if the electrons and holes were not charged, so this diffusion process would be continue uh, continue same as two gases come into contact with each other. Okay, so like it behave like it two gases. Okay, now here, so that what is the diffusion process also not continuous always, so why it will not continuous always, so why it will be stop. Okay, I will explain you. Okay, so see here. However, in a PN junction, when the electrons and holes move to the other side of the junction, they leave behind exposed charge on dopant atom site, so which are fixed in the crystal lattice and are unable to move. See here. Suppose so in this region, so in N region, what happened? So electron will move from N region to P region. Electron will move from N region to P region. So at that case, what happened here? So it will leaves. So if electron is leaving here means, so what happened means some opposite charge is exposed. That means opposite charge is leaved lived beyond that in this position. Okay, if electron is moving from here to here, what happens, so it will be so it will become positive, okay, positive in a crystalline sites. Some positive charge carriers are leaved in crystalline site. Okay, this positive charges doesn't move from one place to another place. Okay, similarly nearer electrons, all nearer electrons leave the positive charge, so at this region. Similarly in the opposite direction also. So if hole is recombined to the electron means what happened here? So here negative charge is developed. Negative charge is developed. Okay. So due to this, here positive charge is developed. Here negative charge is developed. Here negative charge is developed. Okay. So on the n side, so positive ion core are exposed. See here. So on n side, so here positive ion core is exposed, because if electron is leaving means, so here opposite charge is developed. Opposite charge is developed. The charge is developed in the crystalline lattice. Crystal lattice. The charge doesn't move. Doesn't move. So that's why here positive charge will be developed. Positive charge will be developed. Similarly, so in P region, so negative ion core is exposed. Negative ion core is exposed. That means negative charge is developed. Okay. So due to this, so positive charge and this negative charge, what happens? Some space charge region will be developed. Some space charge region will be developed. This region also called as depulsion region. Depulsion region. Okay. See here. An electric field E forms between the positive ion core in N-type material and negative ion core in P-type material. Okay, so here, so positive ion core is developed here and negative ion core is developed here. So due to this positive ion core and negative ion core, some potential will be, so some electric field will be occur. Some electric field will be occur. So due to the thickness of this, so if thickness is more means, so potential difference will be more. So we know already, we know that, so there is a voltage and electric field relation. Okay, V is equal to E into T, like that. So because of this positive charge and negative charge, some electric field will be developed. Some electric field will be developed. Okay, so electric field will be developed. This region is called as depulsion region. Depulsion region. Okay. So depulsion region or space charge region. So we can also call it as space charge region and depulsion region. Okay. Now, since the electric field quickly sweeps free carriers out, hence the region is uh, depleted of the free carriers. Okay, a built-in potential VB due to E is formed at the junction. Okay, so what happened here? Electric field will be developed. Due to that electric field, what happened? There is no free charge carriers. So all free charge carriers will be sweep out from the this space charge region or depulsion region. So due to this electric field, what happened? There is no free charge carriers in this depulsion region. Okay, those free charge carriers are sweep out from the this depulsion region. Depulsion region. Okay, this depulsion region we will also call it as space charge region, and due to that electric field, what happens? Some potential will develop, potential difference will be developed. That potential difference is VB. Okay, so that potential is VB. Okay, so formed due to the electric field. Okay. So this is about the, what is that? PN junction. How junction will be formed? How junction will be formed? So initially, what happened? Electron will move from N region to P region. Similarly, P region to N region. Holes will move from P region to N region. Okay, that is initial process. Initial process. So if electron is moving from N region to P region, what happened? Here, some positive charge is developed. Positive ion core will be developed. Positive ion core will be developed. Okay. Similarly, if hole is recombined with electron, means what happened here? So negative ion core will be developed. Negative ion core will be developed in the P region. So due to this positive ion core and negative ion core, what happened? So some space charge region will be developed. That means some electric field will be developed due to this positive ion core and negative ion core. Some electric field will be developed. That electric field. So due to that electric field, what happened? What is send out the whatever the free charge carriers. If any charge carrier will be there inside the, so this space charge region, so that will be send out due to the electric field. due to that electric field. Okay, so so this electric field, due to this electric field, what happens, some potential difference will be developed. So that's why in between the p region and n region, one barrier will be developed, one potential barrier will be developed. Okay, so now, so what happened after certain time, so those electrons and holes, that is the equilibrium position, that is the equilibrium position. So at that equilibrium position, some potential barrier will be developed in between the p region and n region, p region and n region. So without giving any external voltage, without giving any external voltage, so what, there is no flow of the charge carriers, there is no flow of the charge carriers, because after certain time, so initially diffusion will be takes place, after certain time, so potential region will be developed, space charge region will be developed. So due to that space charge region, there is no flow of either electrons or holes in PN junction diode, PN junction diode, because some junction will be formed, some junction will be formed. Okay, so if you apply the any voltage, if you apply the any voltage, so what happened, so some charge carriers flow will be developed, it depends on the direction of the applied voltage. So without applying any external source, without applying any external source, there is no flow of electrons or holes in case of PN junction diode, in case of PN junction diode. Okay, so this is about the formation of PN junction, formation of PN junction here. Now, so this is the, so diode schematic diagram of the diode. Okay, schematic diagram of the diode or diode representation, simply diode representation. So p region we will call it as plus, so and n region we will denote it as a minus, n region we will denote it as a minus. So p region we will call it as anode, p region we will call it as anode, and n region we will call it as cathode, cathode. Okay, see here the diode is comprised of anode positive side and cathode negative side. Okay, conventional current flow is from negative to positive. Okay, yeah, so this is this direction is wrong. Okay, so depends on the whatever the applied field, that current flow will be depends on it, it's whether it will be depends on forward bias or reverse bias. Okay, so I will explain you what is the forward bias and what is the reverse bias. Okay, so initially here, so this region, anode region, we will call it as, so this is the positive, so cathode region we will call it as negative. So n, that means this is n region, so n region, so is n region is cathode, p region is act as a anode. Okay, so how to remember this means, so cathode means how to pronounce, we can like that, it start from k, like k na. So this cathode, cathode is the, its symbol is the opposite direction of k, opposite direction of k. So based on that, so you can remember this is cathode simply, so this is like a opposite side of k, opposite side of k. So that pronunciation, cathode pronunciation starts like k. Okay, that's why, so we can simply remember that, so this is a cathode. Okay, this is a anode. Okay, so that is about the, so schematic diagram of PN junction diode, PN junction diode. Okay, now energy diagram of PN junction diode. Okay, here, so already we know that, so how p-type semiconductor will behave, how n-type semiconductor will behave. Okay, let us take initially first p-type semiconductor. Okay, so before formation of the PN junction diode, so there is, suppose if you will take p-type semiconductor, so that Fermi level will be nearer to the valency band, nearer to the valency band. Okay, and so before forming the PN junction diode, in case of n-type semiconducting material, so that Fermi level will be nearer to the conduction band, nearer to the conduction band. Okay, understood? So this in case of p-type semiconductor, so that Fermi level will be nearer to the valency band. Okay, so we are not representing the donor level here. Okay, donor level or acceptor level, only Fermi level we are representing. So that Fermi level is nearer to the valency band in case of p-type semiconductor. Similarly, in case of n-type semiconductor, that Fermi level is nearer to the conduction band, nearer to the conduction band. This is before formation of PN junction diode. Okay, so now after here PN junction is formed. Okay, when a p-type material is brought closer to the n-type material, a contact potential VB is developed, which is due to the potential of depulsion region on n side and p side respectively. Okay, so here so some depulsion layer will be developed. So due to that depulsion layer, what happened here? Some barrier, potential barrier will be developed. Potential barrier will be developed. That is the potential barrier, width of the potential barrier equal to VB here. Okay, now so the the contact or behavior of the potential due to n type is Vn and p type is Vp. Okay, let us take here. So due to the n type charge carriers, so there is a some potential will be there, that is the Vn. See here. So here, so this is the n type, due to n type. So here some potential will be developed, that is the Vn. So due to p type charge carrier, some potential will be developed, that is the Vp. Okay, Vp. Now, therefore, at the junction, what is the potential barrier equal to Vn minus Vp? Vn minus Vp. Okay. So now this is the potential junction. How much potential will be occur at the this junction equal to Vn minus Vp. Vn minus Vp. So after the junction formation, the Fermi level becomes common for both types. Okay. So junction is formed. So now junction is formed. Junction is formed means so that Fermi level also. The Fermi level, so before the Fermi, what happened? So that Fermi level is nearer to the, in case of p-type semiconductor, Fermi level is nearer to the valence band. So in case of n-type semiconductor, Fermi level is nearer to the conduction band. Conduction band. So after formation of the junction, what happened? Fermi level is equal to both. Fermi level is equal to both. Okay, so now so see the diagram. This is the p region and this is the n region. So here, so this is the potential difference between both p region and n region. This is VB. This is the VB. This is the potential difference between both p region and n region. This is the what is that energy diagram of PN junction diode. This is the energy diagram of PN junction diode. Okay, so this also you have to remember. So what is the energy diagram of PN junction diode? Okay, remaining we will discuss tomorrow. Okay, so this is about the PN junction and the generation of that means whole electron hole pair and recombination of electron hole pair we will discuss. Okay, yeah. So any doubt means you can ask. Okay, I will take the attendance. So wait one more minute. Yes, if you have any doubts means you can ask, otherwise you can leave from the session. Any doubts?